Hi, I'm Alex and this short video is about solar photovoltaics for small business. I'm going to give you an introduction to solar technology and how it could help your business reduce electricity costs and cut carbon emissions. People in the solar industry use a lot of jargon. So first things first, PV stands for photovoltaic. It literally means electricity from light. When we talk about solar panels, we call them solar modules, and they're made up from individual solar cells. In this module you can see there are 60 individual solar cells in the module. Some modules have 72 cells instead, and the very latest ones tend to have even more. Increasingly we're seeing modules with half-size cells to get better performance. There are lots of different types of solar cells. The most common ones are made from crystalline silicon. Now silicon's a very abundant element, in fact sand is mostly silicon. So we aren't going to run out of silicon anytime soon. This particular module has what they call multicrystalline solar cells. There are some slightly more expensive ones which are called monocrystalline, but these days there isn't much difference between them in terms of their performance. Now this solar module can produce a couple of hundred watts when it's sunny, and quite a lot less when it's cloudy. To get more power from the system, you just add more solar modules, and this makes what we call a solar array. The electrical output from a solar module is DC, direct current. And before we can use this in our buildings, we have to convert it to AC, and that's done using an inverter. The modules in the array connect together, and the DC cables run to the inverter. The output from the inverter is mains voltage AC, and this connects to your building in the same way that other circuits are connected. Most commercial premises have distribution boards, or DBs. That's where your circuit breakers are located, and the output of the inverter usually connects to the electrical supply of the building via a new circuit breaker in one of these DBs. The other job that the inverter does is to synchronize the AC waveform of electricity it generates to the electricity grid. It also has to constantly check that the system voltage and frequency are within the allowed range so the system can operate safely. So, let me explain a little about solar PV system sizing and efficiency. Not all solar modules are the same, and because the output of a solar PV system changes constantly as the sun changes angle in the sky and clouds come over, we need to have some way to compare products so we know what we're buying. The solar industry uses an agreed set of laboratory conditions to quantify the performance of solar modules. These are called standard test conditions, or STC for short. They're mentioned on every solar module datasheet, and the standard test conditions include the level of light, which is called the irradiance, the spectral composition of the light, in other words, the relative level of each component wavelength of light from infrared through to ultraviolet, and the temperature. All of these things have an effect on solar performance. Standard test conditions are equivalent to a clear, bright, sunny day, but because the conditions are so specific, they can't be replicated easily, and they rarely occur naturally. Solar modules are sold according to their electrical power, which is measured in watts peak, or WP. This tells us how much electrical power will be generated when the module is exposed to sunlight at standard test conditions. For a whole solar array with lots of modules, the capacity of the system would be measured in kilowatts peak, or kWp. It's only natural to want to know how efficient a technology is, and the efficiency of solar PV has been slowly but steadily increasing for many years. Nowadays a typical solar module will be about 17% efficient. That doesn't sound too impressive, but when you consider that the sun is a free resource, it puts things into perspective. What the efficiency really tells us is how big a solar PV module needs to be to produce a certain amount of power. The standard test conditions I mentioned earlier use 1000 watts per square metre as the standard level of irradiance for testing solar modules. So if a solar module has an area of 1 square metre and can generate 170 watts of power at STC, then it would be 17% efficient. The latest solar PV modules can be a little more efficient, but the price starts to climb up quite quickly. So if you're looking for value for money, you need to find the sweet spot. Luckily, solar PV installers take care of this and will normally stick to 1 or 2 tried and trusted brands. So, where can I install solar PV? Well, to get the best from a PV system, you ideally need a roof that faces towards the south. If you have a flat roof, then you can still install solar PV, but the modules will need jacking up a little on frames, so they have a better angle. When it comes to angles, there are two angles that are important. First is the orientation with respect to south. Sometimes this is called the azimuth. Due south has an azimuth angle of 0, and for everyone in the northern hemisphere, this is the best orientation for a solar array. Due west is normally plus 90 degrees and due east minus 90 degrees. But you need to be careful because some software applications actually do it the other way around. The other important angle is the slope. Sometimes we call this the pitch. If you're putting solar PV on a sloping roof, then the slope is pretty much fixed by the slope of the roof itself. But if you're putting the modules on frames on a flat roof, you have a bit more choice and you can get frames that are set at various different angles. Imagine it's the winter time. The sun is quite low for most of the time. As long as it's not cloudy, you're actually best off with the solar modules jacked up quite steeply so the sun strikes them at a better angle. On the other hand, when it's summertime and the sun is quite high in the sky, you want the modules fairly flat. Obviously you could have a fancy system to adjust the angle, or even a setting that you change occasionally, but that flies in the face of the inherent simplicity of solar PV, and it brings a whole host of extra complications that are best avoided. So as you can imagine, there'll be an optimal pitch that gives the best overall energy generation. When it comes to working out the best angle for a system on a flat roof, you have to consider both the azimuth and the pitch of the array. If the pitch is quite steep, it's more important that the array is accurately aligned to south. On the other hand, if the modules are flat, north or south become irrelevant. In practice, you wouldn't want your modules completely flat, because they would build up a lot of dirt and residue from dust and rain. But systems with a shallow pitch are quite popular, because you can pack more modules into a given space. What we really care about is how much energy the system is going to generate over a given time, usually a whole year. We can use software to work this out for different azimuth and slope angles, but the results also vary depending on where in the world your system is located. That's because the sun rises higher as you get nearer the equator. For the northeast of England, you get a distribution like this. The chart shows that an orientation of south with a slope of 35 degrees gives the best results. If we call this 100%, the relative energy yields from other combinations of azimuth and slope can be read off from the chart. So for example, an east-facing array on a roof sloped at 60 degrees will produce about 65% of the energy of a south-facing roof sloped at 35 degrees. Now what I've showed you so far assumes that your solar array isn't going to be shaded by trees, buildings, or indeed the horizon itself, if there's higher ground to the south of your building. This is really important because PV systems can lose a lot of their energy yield if they are frequently shaded. The extent of any shading varies over each day and over the course of the year, so we tend to use software tools to quantify and analyse what impacts the shading could have on the energy yield. This clip shows an example of how the shadow positions change across a day, and it's during one single day in July, and again during one single day in February. We can use sophisticated software tools to accurately determine how much impact shading is likely to have on your solar PV energy yield. So we've looked at the technical aspects of solar PV, but what about the commercial side of things? The good news is that the cost of solar PV kit has fallen dramatically in the last few years. Unfortunately, the financial incentives to install solar PV have also fallen, and there's no longer any feed-in tariff. Instead, there's an incentive called the Smart Export Guarantee, which gives you a small payment for electricity that you export to the grid. The biggest benefit, however, comes from utilising the solar-generated electricity within your own building, because that reduces the amount of electricity you have to buy, and it also reduces your greenhouse gas emissions. If you've got a site which has a decent-sized, unshaded, south-facing sloping roof, and you'll use a large proportion of the electricity you could generate within your own site, you could expect to get a payback time of around 7 to 10 years from solar PV. And that's not bad, because you can expect the system to work reliably for 25 years or so with minimal maintenance. I hope you found this useful. You can find more information about solar PV by downloading our fact sheet. Or if you're interested in other technologies, we have more videos available. Thanks for watching.